Good morning, everyone. My name is Scott Bassett. I'm on the XR graphics team. I have another colleague here named Rob who's going to come up later and talk about a separate section. So over the next hour, we're going to go over basically how all of the XR graphics stuff works in Unity and also some best practices. So let's begin with a little bit of review. Or actually, let's go over an outline first before we get to the review. So first, we're going to do a little review. And then we're going to move into the different stereo rendering methods that Unity supports. Then we're going to talk about RenderScale versus RenderViewportScale. After that, Rob is going to come up and talk about post-processing. And then we're going to talk a little bit about what we're doing for 2017.3. And then finally, we're going to wrap up with the Q&A that you guys might have. So let's begin with the review. So in Unity 5.6, we added support for Android single pass. This drastically cuts down the CPU utilization on Android. There's a little asterisk next to it, though, because a lot of the graphics drivers on the phones are broken. So it's not very useful at that time. But as of Android O, it at least works on Pixel perfectly fine. Then in Unity 2017.1, we added support for NVIDIA VRWorks through a plugin that you can get through an asset store. We also added support for native cube maps. So if you're doing video playback and stuff to that extent, you can use that. We also added this really cool thing called the mock HMD Vive. And what this does is it simulates all the settings of a Vive without actually having one, so you can test stuff easily with it. And we've had a dedicated effort to improve quality of just VR rendering on Unity. In 2017.2, we were adding support for macOS, Windows MR. We've added a new stereo rendering method called single pass instancing, which I'll get into a little bit later. We've obsoleted camera.stereo mirror mode, and the reason for this is because all the headsets are actually asymmetric, so just copying the image from the left eye to the right eye doesn't really work. It used to work on Oculus because they were padding the frustrums, but it was wasting perf. And additionally, we've been working on improving quality again. So let's get into the different stereo rendering methods that we support in Unity. So at first, here's the scene that we're going to be going over with. You can see there's a red cube and a green sphere and just the camera. So it's a very, very simple scene. So the first one we'll start with is multipass. So what happens is when you're on the camera, or when you go through the scene, we first start on the camera, and we have the texture that represents the eye attached to it. And the white bounding box is the frustrum. So then we go to the cube and we draw the cube, and then we go to the sphere and draw the sphere. And then we go to another texture that represents the other eye, and we do the same thing. We go to the cube, render the cube, and we go to the sphere and render it. So you can see we're going through the scene graph twice here, and also we're not really sharing any GPU work across the two textures, so this is our least efficient one. However, this works with most people's apps by default, so there's not a lot of changes you have to do for this. So the next one I wanted to talk about is single pass. This was introduced in Unity 5.4 for PS4 and PC. And what we have here is we have two textures, but they're packed into one bigger texture. So we call this double wide internally. So what we do here is when we go to draw the first object, we set the viewport to the left side, and we draw the cube. And then we switch the viewport to the right side, and we draw the cube again. And then we go to draw the sphere, but we've already set the viewport once, so we can just reuse it and draw the sphere there. And then we ping pong to the other side and draw the sphere here. So in this example here, you can see that we're only going through the scene graph once, so this is much faster on the CPU. However, there's a lot of extra GPU state changes that had to be done to accomplish this. So in Unity 2017.2, we're adding a new rendering method called single pass instancing. The caveat with this is it's only available on Windows 10 with Direct3D 11 and recent graphics drivers. However, on PC, most people are running on Windows 10 already, according to the Steam survey and stuff to that extent. And they already have the prerequisite GPUs for doing VR on PC. And what will happen is if the extension is not supported, we'll switch to multipass, so your apps will still work. They'll just run a little bit slower. This is also the only way to do single pass on HoloLens, so that's a good thing to keep in mind. One issue with it, though, is draw procedural indirect. What this function does is it uses a compute buffer to do pass all the arguments for the draw. However, what we do with single pass instancing is just issue instance draw calls. And since this is getting all its information from a compute buffer, you have to manually go change that yourself. Finally, I didn't really cover it a lot, but Android single pass is pretty much the same as this. So anything that applies there applies to here. So it's very useful for porting your game over. Finally, we're going to bring this to PlayStation 4 in 2017.3. So that'll be relatively soon. So let's go over how this works. So here we have two textures again, like in the first example, the multi-pass one. However, the difference is these are both in one texture array. So they're just two slices of the same texture array. So when we go to set the viewport, it automatically gets applied to both slices. And then when we go to issue a draw, we issue an instance draw that's twice as much as normal. And depending on the instance, we determine which slice of the texture to render to. So you can see here we render the cube, and then we move on and we render the sphere. So you can see here we did the same amount of work, but in a lot less calls and CPU work. So this is actually a lot more performant. So let's get into the performance. Actually, let's go to the Vertex shader changes first, then we'll get into the performance. So here's like a very, very simple Vertex shader change. This Vertex shader just takes in the position and transforms it into clip space and then returns that value. So let's go through the steps necessary to update this to support single pass instancing. So the first one is you need to add this macro, Unity Vertex input instance ID. And all it does is it just says uint instance ID is equal to the system value for the instance ID, which is a built-in HLSL variable. And then next, in your output, you'll put Unity Vertex output stereo. And all this does is it declares a stereo index, which uses another system variable, which determines which slice of the texture array to render to. And then in the Vertex shader, you just call Unity setup instance ID, which will take the instance ID and pipe it through to Unity stereo index. And then finally, you just say Unity instance Vertex output stereo, which will just pass the stereo index into the output stereo index. And we would really recommend that you guys use these macros, because if we need to change anything, it'll automatically work for your shaders if you're using these. If you're not, then you're going to have to go modify your shaders yourself manually. Additionally, you can see that it was very simple to do this, and we've already updated all of our built-in shaders to support this. So the Fragment shader changes are even simpler than the Vertex shader. All we need to do is just unpack the stereo index into Unity stereo index, and we do that through this variable macro Unity setup stereo index post Vertex. And that's all you need to do. Let's get into perf a little bit now. So the scene that we're going to use for perf is Viking Village. This is a deferred shading example, even though we prefer everyone to use forward shading. And you can see right here we're using an Oculus with an i7 6700 at 4 gigahertz and a GeForce GTX at 1080. This is a really powerful machine, as you can see. And we got all these perf measurements using Oculus's built-in perf tools that they have. So here's the graph of the different stereo rendering methods. So multipass took 4.8 milliseconds on the CPU for this test scene. The GPU was 6.4, and then single pass, the CPU was 3.8, and GPU 6.1, and single pass instancing was 3.5. So you can see the CPU utilization is going down a lot. The GPU one isn't going down as much as it could be. We're working with the other companies like Oculus and Valve to get that down even further. It requires a little bit of changes on their side. So moving on, I'd like to talk about RenderScale versus RenderViewportScale. These terms are very similar, so it leads to confusion. So hopefully this will help clear it up. So we have here just a simple one eye of a set of texture for one set. And we're going to go from 1 to 0.5. And when you use RenderScale, what will happen is we'll actually delete this texture. And then we'll create a new texture that's a quarter of the size, because it's 0.5 in each dimension. So this is an expensive operation to do dynamically while your game is running, and that's why we have RenderViewportScale. So with RenderViewportScale, when you go from 1 to 0.5, what will actually happen is we'll just set the viewport to a smaller portion of the same texture and just render to that. So this is much more efficient. However, due to us using only a portion of the texture, there's some issues that come along with that. And Rob is going to come up here later and discuss those with you. So just to recap a little bit about RenderScale versus RenderViewportScale. RenderScale is actually deleting and creating new textures, so it's somewhat time-consuming, while RenderViewportScale just modifies the viewport. To help alleviate some of the confusion between the terms, we've actually renamed RenderScale to iTexture Resolution Scale in 2017.2. And RenderViewportScale isn't supported when using deferred rendering because of the G buffers and stuff to that extent, so please don't plan for that. And like I already stated, but scale is applied to both dimensions, so a value of 0.5 will actually lead to a quarter size image, so please keep that in mind. Now I'd like to bring up Rob to talk about post-processing for XR.
Thanks a bunch, Scott. So as you mentioned before at the beginning, I'm Rob, and I work with Scott in the XR graphics team. So I'm going to talk to you about XR and post-processing. So just like other parts of the graphics pipeline, extra considerations need to be made to handle post-processing correctly in XR, because XR is a special snowflake. So I'm going to try and iterate over some of those issues and how to address them. So we'll chat about intermediate render texture allocation, screen versus texture size, shader scaffolding, and some other random bits. So the hope is that we'll familiarize the problem set enough for you so that if you run into some similar situations, you'll be able to fix them on your own. Just an extra note is that though this portion is applicable to post-processing in general, most of what I'm going to be talking about is in the context of post-processing Stack V2. And I just wanted to shout out the post-processing team for doing really outstanding work. And I think everyone here has seen what an impact they've been making here with Unity. So often with post-processing, you're going to need an intermediate render target in order to render an effect. So we want to create these intermediate render targets that match the source target in size and possibly in format. So with double wide, that texture is going to be at least twice as wide as the individual eye portion. And then when you're using stereo instancing and Android single pass, we need to make sure that we're using a texture array, right? So we have one slice per eye. So instead of magical incantations to generate the correct screen space texture format, we expose iTextureDesc in XR settings. This is in 2017.2. So what this is going to do is it returns a render texture descriptor sourced from the engine XR texture manager. So it's configured to match the engine managed textures. We can also query the render texture descriptor from a source texture if that's available. So if you're using the legacy on-render image infrastructure, you'll have that source texture, and you can grab the descriptor right out of it. So usually when you're allocating temporary render targets or render textures, you kind of pass in these lists of arguments, and then you get your temporary target back. So instead what we're advocating is you want to use this descriptor. This is a simpler API. It matches actually what the underlying APIs do themselves. And this is what Unity is doing underneath the hood for you anyways. So if you pass in a big list of arguments, it's going to package them up in a render texture descriptor and then pass that into the core engine. So you might as well manage this on the script side instead of having this intermediate layer do all the munging. So here's like some original boring code. So here we're like saving off the camera pixel width and pixel height, and we're going to use this later for texture allocation. And this is what it's going to look like for with the new XR path. So if stereo is enabled, we're going to grab iTextureDesc from XR settings, and then we can source our width and height from that descriptor. And we're also going to save off the descriptor for usage later. So let's take a look at actually what it looks like to allocate a render texture using this infrastructure. So in the old style, what we were doing is we would have a width and height that we grab from our post-process render context. Then we have our format, our color format, our read-write mode, our filter mode, and then we pass those in when we're getting a temporary target. So here there's two targets being allocated. One is could be running at quarter resolution, and then the other one's at full size. So you can see the explicit list of arguments being passed in. So instead, if we use a descriptor, what's going to happen is we'll fetch the descriptor from the context that we cached off, pass in the extra modes, like our extra color format and a read-write mode, and it's going to return a new render texture descriptor that matches the XR configuration. And then in order to do the scaling, what we can do is apply that same TS value to scale the width and height to quarter resolution if needed. In practice, I just kind of have this slide to show like what the exposed code would look like, but we don't really want to do this either. We kind of want to hide this stuff behind the post-process render context as well, which is what this looks like. So instead, there's a new API in the post-process render context called get screen space temporary RT. And what you do is you can pass in those arguments again that you'll be using to generate the screen space render target. And if you need to know if you need to override the width and height, you can pass those in. Usually when you're doing screen space arguments, you're using the same dimensions as that input texture, so you don't need to modify it. And there's a lot of flexibility here for default arguments, so you can skip all those things. All right, so now we can talk about logical eye screen size. So there's going to be a difference, especially for XR rendering, between the physical render texture size and the logical screen eye size, right? So for intermediate allocation, you want to use this eye texture descriptor we've been talking about, because that's going to be allocating those physical textures. But if you have any script or shader logic that's based on the screen size, the logical screen size, so something like if you're using the screen size parameters in a shader, or you're building a texture pyramid, you want to base this off the logical size. And in this case, you can use XR settings.iTextureHeight and XR settings.iTextureWidth. So these represent per eye texture sizes that you need to know if you need to know the size of the screen that's being operated on. You might think for like, okay, if we're running double wide, why not just grab the width out of the descriptor, cut it in half, and use that? This is actually not going to be the same. So if you run through the script and you debug, the values aren't the same. And the reason is the descriptor, for the purposes of texture allocation, actually it doubles the width and then pads it a little bit to make sure that it's appropriate for MIP mapping. So these values are not, like, from the face, they may not be the same. So previously, what I would do is I would actually kind of had this like voodoo code to try and determine what kind of width I really wanted to have for my screen width. So on the top part of that branch, if I think it's double wide, I'll just divide the width by 2. Otherwise, I just use the width from the descriptor. But instead of all that, we can just source the screen width directly from iTextureWidth. And then we use it for something like a screen ratio. So we need to pass aspect ratio into the shader. All we have to do is just use our screen width and screen height, and those values will be right. All right, shader changes. So when we're working with stereo screen space effects, we have a decent amount of extra work to do. Are we sampling and outputting to the correct eye? Are your texture coordinates adjusted for the eye? Are you taking RenderViewportScale into account? And are your neighborhood samples clamped appropriately? And a couple other things, right? And in Unity, we try and provide a set of tools that help you with these issues. So starting with every programmer's true love, texture coordinates, we have a pretty simple question to ask. Are our texture coordinates correct for stereo? And are they sampling from the correct eye? So for double wide, we want to make sure we're sampling from the correct half. And for instancing and Android single pass, we want to make sure that we're selecting from the correct texture layer. So when you are sampling from a double wide texture, you need to make sure your texture coordinates are sampling from the correct half that corresponds with the current active eye. So we need to have some kind of texture coordinate corrector that's operating per eye. We have 2 tools for this. We have the transform text macro, and we also have Unity stereo scale offset, along with some helper methods that go with it. So transform text is an existing Unity macro that works with those ST properties that you've seen in Shader Lab. Usually you see this associated with main text ST. So what the macro is doing is it grabs the ST property, and what it's encoded with is in the XY, it has scale values, and then in ZW are offset values. And so the math is pretty simple. It takes an input texture coordinate, it applies the scale with the multiply, and then adds the offset. So what you'll do is you'll have your normal texture coordinate pass into transform text, and then it'll spit out the corrected texture coordinate. That's stereo aware. Let's see. So these ST properties are populated if you use graphics.blit or command buffer.blit. In this case, main text ST is always populated no matter what. And then other ST properties that you have will also be filled in if they correspond with an XR texture. So when these XR textures get allocated, they have a VR usage. And if those VR usages say if it's 1 eye or 2 eyes, then it'll also get this ST property populated. The drawback with this is that it doesn't actually work with custom blit procedures. So if you wrote your own blit, you're not going to get this ST property filled in. And this actually happens in post-processing stack v2 because it has its own blit full screen triangle process. Let's look at the other tool, which is Unity stereoscale offset. So Unity stereoscale offset is an array of float 4s that lives in the single pass constant block. So this is Unity stereo globals if you've surfed it all inside of the Unity standard shader set. And we index into this with a Unity stereo index. So I'm just going to quickly jump over into what Unity stereo index is and how it's populated. So for double wide, Unity stereo index is bound before each draw. So since it's put in a constant buffer, and then each draw gets the correct eye updated. So the left eye will draw, and before that left eye value will be put into the constant buffer. Right eye draws, right eye value will be put in the constant buffer. So you know for all the shader instances will know that for all the draws it's using, it can go look in the constant buffer and find the correct value for Unity stereo index. For texture arrays, it works a little differently. So instead of sourcing it from the constant buffer, it gets decoded from the instance ID. So that's what Scott was talking about earlier. All that scaffolding is populating Unity stereo index correctly for you to use. In the end, when you're writing your shaders, you don't have to worry about how it's getting filled in. You just know that Unity stereo index is correct for whatever draw you're using. So once we know Unity stereo index is populated correctly, we can use it with full confidence that it's selecting the right element out of Unity stereoscale offset. Looking at the helper function, you see that the math is basically the same as transform text. It applies a scale and then adds an offset. And that's about it for this. So there are drawbacks for Unity stereoscale offset, though. Unity stereoscale offset is only available for single pass. So if you want to use it, just use the helper methods. The helper methods are going to automatically handle populating the function or knopping out if you're not running in single pass. You might be thinking, okay, why do you have two solutions for the same problem? This really doesn't make any sense. And the archaeology behind this is that the original infrastructure meant that Unity stereoscale offset was meant for normal rendering, for normal object rendering, and then main text ST was supposed to be used for post-processing. But if you're not using the built-in blit procedures, you don't get to take advantage of that infrastructure. So that's kind of how we got into this issue. So this is how you use these helper functions. So just very similarly to transform text, you have your input texture coordinate, you feed it to the helper function, transform stereo screen space text, and out comes a corrected texture coordinate that's stereo aware. So this is what a bug looks like. So some of you may have seen this when you're doing your own rendering. You get this kind of doubled up pair of eyes when you're running single pass. So we're going to go over what's actually happening when this goes wrong. So on the left, we have our source texture. And we have our left and right eye each occupying half of the texture. And then it's getting copied into our destination texture, but it's getting doubled up. And the reason is that even though for the destination texture, it's copying into the correct eye portion, its texture coordinates aren't being sampled or aren't being generated correctly, right? So it's copying into, for the left eye, it copies into 0 to 0.5 for X, but it's sourcing the samples from 0 to 1. So I have this little color coding. So you can see blue is left, green is right, and you can see how that the sample range is going from 0 to 1, but the copy range is 0 to 0.5. And then the same thing happens for the right eye. So instead of copying just the left and right, for both, we're doing a double copy. And so then this produces this artifact. And then if you have multiple post-process effects and you have the same artifact, it turns into this like crazy hall of mirrors. So instead, if we make sure that we're correcting our texture coordinates, we see that we'll sample from 0 to 0.5 and copy to 0 to 0.5 for the left eye, and then sample from 0.5 to 1 and copy from 0.5 to 1 for the right eye. And then you see the color coding matches. So blue's getting copied to blue, green gets copied to green, everyone's happy. What about texture arrays, right? So double wide has its own suite of problems. Texture array has a couple things you need to take care of too. But it's not as complicated as double wide. So when you're using texture arrays, which come up for single pass instancing and Android single pass, we have two primary things we need to worry about. Since they're texture arrays, we need to make sure that they're declared correctly, and we need to make sure we're sampling from the correct slice. So let's talk about that, the texture declaration. So the shader languages themselves treat texture arrays differently than a normal texture. So you need to make sure they're being declared correctly. So all this macro is doing here, this Unity declare screen space texture, is it's making sure that it calls the 2D array texture declaration if you're using instancing or Android single pass, which up there is mentioned as multi-view. That's the underlying extension. Otherwise, it can just call a normal 2D declaration. So now that we've declared the texture correctly, how do we make sure that we're sampling from it correctly? So what we need to do is, similarly to double wide, we need to sample from the correct eye portion. And those eye portions are placed into the slices of the texture array. So what we can do here is we can use Unity stereo eye index to source the correct slice. So by the time it gets to either the Vertex or Fragment shader, it should be aware of Unity stereo eye index. And so using that, it'll be able to index in the correct portion. It'll have Unity stereo eye index populated correctly, and then you can use that to index into the texture coordinates. So for a 2D texture array, that third texture coordinate is actually the array slice selector. And this is just like a super basic example of how to use those macros. So when you declare your textures, just make sure you use that declare screen space texture macro, and then sampling, wrap it in Unity sample screen space texture, and it'll automatically inject that slice for you. All right, render viewport scale. So this is a source of great consternation. How are you supposed to manage render viewport scale? So as I mentioned before, the ST properties only work with command buffer.blit and graphics.blit. And the ST properties actually do take render viewport scale into account. On the other hand, Unity stereo scale offset doesn't offer support. So if you're not using the existing infrastructure of these blit methods, you know that basically nothing in that setup is going to support RVS for you. So what are you supposed to do? So if you have something like post-processing stack v2, what are you supposed to do? And then for me, I decided to roll my own support into that library. This is actually pretty reasonable to do with post-processing stack v2. I thought it was going to be pretty complicated, but it was actually really, really easy. So one great thing about post-processing stack v2 is it has its own shader infrastructure. So that makes it really easy to override. So the two bits of plumbing that we need to do is, on the shader side, we need to create a new constant that takes the render viewport scale value into effect. So I'll just create a new constant called RVS global, and there's a header file called xrlib.hls so that I can jam it in. And I'm going to rework transform stereo screen space text to use RVS global. And on the script side, we need to make sure that we're passing in the render viewport scale value through that constant. And we have infrastructure for that too, shader.setGlobalFloat. And these are literally all the changes you have to do. It was actually way easier than I thought, and everything kind of worked. So shader side, I'm declaring RVS global as a float, and then all I have to do is multiply it against the scale offset. So I fetch that scale offset from my Unity stereo scale offset array, and then multiply the XY scalars by RVS global, and now everything is correct. On the script side, I need to make sure that RVS global is being populated correctly, and I source that from xrsettings.renderViewportScale. And just to be clear, like I have that around with stereo enabled is doing a check there. If I just use RenderViewportScale like willy-nilly, it'll return values that you don't expect. It's going to return 0 if you're not running an XR. So be careful you're not using it just everywhere. So in the actual code, I have a branch in there making sure that it sends in 1 for monoscopic or just for monoscopic. So again, just like the double wide texture, this is kind of what bugs look like when you're using render viewport scale and you're not correcting your sample coordinates. So this can be pretty confusing to look at. I know when I'm looking at RenderDoc, I'm like, I have no idea what's happening when I see this sort of thing. But actually, when we clear it up a little bit, it makes sense. So instead of having all the images, we're going to look at just like the left eye of the source texture. So this red box here represents the left eye portion of the texture, but the green box is representing what's actually valid for the rendering. This is the portion specified by RenderViewportScale. So in this case, we're using a RenderViewportScale value of 0.6. So our left eye portion, the left eye texture portion goes from x0 to 0.5 and from y0 to 1, but the RVS portion is only 0 to 0.3 for x and 0 to 0.6 for y, and that's what the little text on the bottom is indicating. So you can see that not the whole left eye texture portion is being used. By default, when Unity is rendering, it doesn't actually clear out the unused portion, which is why it looks more confusing in the other image. We'll go to back to what it looks like. So that red eye texture, or the red portion of the texture that's not valid doesn't get cleared. So when you start to look at it in tools, you're like, what the heck is going on? It has all this extra junk in there. And those are artifacts from previous frames that had different values of RenderViewportScale. When the texture gets actually presented, only the valid portion is blurred out, ideally. So then the user doesn't actually notice this. But when you have bugs, you're actually sampling that red portion as well, which is exactly what's happening here. So if you do a blit and you're not taking RenderViewportScale into account, you actually are copying that whole texture portion. So again, we have a texture portion and a viewport mismatch. And these arrows are kind of helping show what's happening. So we copy that whole thing over to that shrunken down viewport. And so we start to kind of have this, again, this Hall of Mirrors effect. So then when we factor in the previous eye artifacts, now instead of having the valid viewport and basically the trash that you're not supposed to be worried about, now you start to have valid viewport, trash from the other texture, and then the trash from its own texture, right? And now this gets quickly out of hand, and it can be, sometimes actually it's even worse because the texture coordinates may start to ramp and then go to the top, and you'll have like 3.5 portions of a texture, and then if this starts to happen, you're like, I have no idea what I'm rendering anymore. But then when you jump into RenderDoc or whatever graphics debugging tool you use, it'll start to make a little sense. So hopefully now when you see this, you'll be like, oh, I know exactly what's happening. And you can start hunting around in wherever you're doing your blitz and making sure something is corrected. So when we do correct for RVS, we see that we sample from the green portion and then copy into the green portion. So using the color-coded texture coordinates and the destination normalized viewport coordinates, we'll see that they're matching up. We still have our previous frame artifacts, so you're going to see these when you're debugging. But in the end, we're going to only display the RVS portion of the texture. Stereo clamping. So this comes up if you're doing any kind of neighborhood screen space samples in a shader. So you want to make sure that you don't accidentally sample the wrong eye in single pass double wide, or outside of the valid RenderViewportScale area. So this is what Unity Stereo Clamp is here to do. So all it's doing is it's basically clamping the coordinates to the correct portion of the texture. I think I have a little artifact that didn't say X. It's just coordinates. And the way it does it is just very similar to that same correction with RVS Global. So it grabs the scale offset, applies RVS Global, and then uses that scale offset to do the clamping. So it's extremely easy to use. The only bummer with it is that it does require manual inspection. You need to know where in your shader that you're doing your neighborhood sampling. So assuming you have been writing your own post-process effect, then hopefully you know where you're doing your neighborhood sampling. In our existing infrastructure, we're trying to get all this stuff ported over. So basically, anytime if you're offsetting from your interpolation generation texture coordinate, you probably need to use Unity Stereo Clamp. Sometimes this ends up with artifacts because you can accidentally end up, not accidentally, but when you get to those edges, you'll start sampling the same texture coordinate, and it can sometimes end up with unexpected rendering, but that'll be the same thing at the edge of a normal texture too. And don't use this in the Vertex shader. You want to use this. You want to use this when you actually do a texture sample. So don't pre-correct your texture coordinates. So these are a couple simple uses. Like if we have a jitter value, we just wrap the whole thing in Unity Stereo Clamp, and then there's a more complicated example on the bottom, right? So there's a big neighborhood sampling from like a quadrant pattern. I don't know. I should have probably drawn something instead. So a couple extra bits. When you're using post-process effects, it can be really easy to get carried away because they're great and they're really fun to use. I know I have a lot of fun using them and messing around with the different looks that I can generate with the post-processing stack. But you need to make sure that they're actually appropriate for XR rendering. If you're doing any kind of temporal effect, this can introduce latency and blurriness, which is not pleasant for the XR experience. And if you're using an effect that's kind of simulating a physical camera property, does that really make sense for a headset that's simulating the human eye vision, right? You don't want to do that sort of thing. So even though depth of field is super cool, do you really want to use that in your VR headset? Probably not. No one's going to stop you, but just think about it. If you are using multipass and you have some kind of set of history textures, you're going to need to have one set of history textures per eye. The reason is because we go through the scene graph twice. What's going to happen is you're going to go through that this post-process effect twice as well. So if you keep just a history texture and you populate it with the left eye, if you don't keep a second set, when you do your right eye render, it's going to source its history from the left eye. So then you start to get ghosting from the other eye. So I probably should have a screenshot, but yeah, if you have ghosting and you're like, oh, it looks like two eyes are being rendered in one, it could be accidentally sampling from the other eye, from a history texture from another eye. And then when I'm running into problems, I tend to toggle between the different stereo modes because that can kind of give me an indication of where my problem is happening in my stack. So usually I'm running in single pass and ideally instancing, and if I see something wrong, I can just jump over to multipass to do a verification. You can see the examples of this work on the post-processing GitHub. So if you go over there, there's this branch called XR Update. And so that's where I've been doing a bunch of these changes. And this is a pending PR to land into the mainline V2. But it's kind of nice to go and look at a bunch of examples. Like basically, I just went through every effect in the post-processing stack and tried to update it for XR. So you can see what kind of different problems I ran into and how I fixed it. And the commits have some comments, so hopefully it'll be useful. All right, I'm going to get Scott to come back up here and finish off the presentation.
Okay. Thanks, Rob. So I'm going to talk a little bit about Unity 2017.3. In particular, as you can see from Rob's talk and all the other stuff we've discussed, there's a lot of specific stuff you need to do to properly support XR. So this is a really good example of one of those situations. So I have this video here. How do I even play it? Okay. Of the terrain, and there's some billboard trees that are placed on this terrain. And if you look at the top of the tree where all the leaves are when I play this video, is it going to work? You should see them like rotate really strangely. Is this it? Oh wait, sorry. I went to the wrong slide. Wait a second. Oh, dang it. Oh, it does sound too. Oh wow, Safari quit. Awesome. Hold on a second. Oh no. My mouse died. Ignore. Oh, it's not showing up again. Awesome. Here, let's do this then. I'm going to turn off this mirror built-in display. That'll make it easier. Safari. Slides. XR graphics. Presentation. Okay. Start here. Okay. There you go. So if you look at the leaves of the trees, you can see them start rotating a lot. Particularly, watch, I'll move up and down here in a second. So it looks really strange, right? this is how the trees were in Unity, and if you particularly look at this in VR, it's really noticeable. So to fix this in 2017.3, we actually had to write like a new tree renderer to properly support this. So as you can see, they're fixed now, but this was quite an involved process. So please keep this in mind when you do stuff for VR, that it's not obvious how you need to fix stuff always, and it does take time. So that's all there is on that. So moving on, let's move on. I just wanted to call out our documentation. So we have various pages in the documentation that cover all these different topics we discussed today. Right now, the single pass instancing one was only for HoloLens, but all that same information applies to PC now, so you can just read that if you need to. We're actually also updating the documentation to be even better than it currently is. So that wraps up our presentation. Does anyone have any questions? Please step up to the mic now. It would be great. Oh, Rob, could you please come back up here, too? No questions? Awesome.
Yes, all problems are solved.
Okay. All right. Thanks, guys.